Hello and welcome to Bedtime Science. I'm glad you're here tonight. Maybe the day was a little too loud, a little too fast, or maybe you're simply someone whose mind needs something vast and quiet to settle into before sleep finds you. Either way, tonight is yours. Let your breathing slow and let your body sink a little deeper into wherever you are right now. Because tonight we're drifting into the deep cosmos, past the light of familiar stars, past the edges of what telescopes can see, into a darkness where the rules we trust begin to bend, and the universe keeps secrets it has never shared with anyone. Tonight, you'll learn why 95% of the universe is completely invisible, and no one knows what it's made of. You'll hear about a strange cold scar in the oldest light we've ever detected, one that some scientists believe was left by a collision with another universe. And you'll discover why, across billions of potentially habitable worlds, the cosmos remains eerily, impossibly silent. Over the next 2 hours, we'll drift through 100 of those secrets. Stars that shouldn't exist, signals from empty space, galaxies that vanished without a trace. Each one a quiet mystery, unexplained, unresolved, and waiting in the dark. And just before we begin, if these calm explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. Now, let's begin. Our first mystery begins with something you cannot see. Right now, all across the universe, galaxies are spinning. Vast spirals of stars, turning at speeds that should tear them apart. The math is clear. At the rate they rotate, stars at the edges should be flung out into the void like water off a spinning wheel. But they aren't. Something is holding them in place. Something with mass, something with gravity. But something we cannot see. Scientists call it dark matter. It outweighs everything visible in the universe by roughly 6 to 1. Every star, every planet, every grain of dust you've ever known is outnumbered by something we have never detected, never touched, and never identified. It's everywhere, and we still don't know what it is. And that invisible force is only part of the story. Because after the Big Bang, the universe expanded. That much we expected. What no one expected was that it would speed up. Imagine throwing a ball into the air and watching it rise faster and faster, never slowing, never coming back down. That is what the universe is doing. Every galaxy is drifting away from every other galaxy, and the space between them is stretching at an accelerating rate. The force behind this has a name, dark energy, but the name is almost all we have. It appears to make up roughly 70% of all the energy in existence. It is the dominant force shaping the cosmos, and its true nature is completely unknown. Now, somewhere in that deep, expanding universe, something screams. Not in sound, in radio waves. A burst of energy lasting just a few milliseconds, so brief you could miss it between heartbeats. But in that sliver of time, it releases more energy than our sun puts out in an entire year. These are called fast radio bursts. The first one was detected in 2007, buried in old telescope data. Since then, hundreds more have appeared. Some come from dead, quiet galaxies where almost nothing is happening. Others erupt near violently spinning neutron stars. They show up in completely different environments, which means there may not be one explanation. There may be many, and so far none of them are settled. But let's go back further, much further. When the universe was about 380,000 years old, it released a glow. That glow is still here, a faint wash of microwave light filling every direction of the sky. It's called the cosmic microwave background, and it is almost perfectly uniform. Almost. In the southern sky, there is a patch. It's colder than it should be. Not by much, a tiny fraction of a degree, but across such an enormous area that the odds of it occurring by chance are troublingly small. Some physicists think it may point to unknown physics. Others have suggested something stranger, that it could be a bruise, a scar left behind by a collision with another universe, pressing against our own in a time before time had meaning. And if you look toward the constellation Eridanus, the mystery deepens. Because right behind that cold spot lies one of the emptiest places in the known universe. A void stretching nearly 2 billion light-years across, where galaxies are strangely scarce. Some researchers thought it might explain the cold spot. Light passing through such an enormous emptiness could lose a tiny amount of energy, arriving slightly colder. But when they ran the numbers, the supervoid wasn't enough. It could account for part of the temperature dip, but not all of it. So the mystery doubled. Why is the cold spot there? And why does one of the largest empty regions in the cosmos sit right behind it? Here is something that can quietly rearrange the way you think about reality. Everything you have ever seen, every star in the night sky, every planet, every ocean, every atom in your body, accounts for roughly 5% of the universe. 5. The other 95% is something else. About 27% is dark matter, the invisible scaffolding holding galaxies together. The remaining 68% is dark energy, the force stretching space itself apart. We live inside a universe that is almost entirely made of things we cannot observe, cannot explain, and have never directly measured. We are the rounding error. Now remember those fast radio bursts, those millisecond screams from deep space? Some of them may have an address. A magnetar is what happens when a dead star refuses to be quiet. It's a type of neutron star, a collapsed remnant no wider than a city, but with a magnetic field 1 trillion times stronger than Earth's. Strong enough to distort atoms into thin needles. Strong enough to be lethal from 1,000 kilometers away. And in the neighborhoods of some magnetars, fast radio bursts have been detected. But even knowing this, scientists cannot fully explain the mechanism. How does such a clean, bright, impossibly brief pulse emerge from such chaos? The magnetar keeps its secret. Let's return to that ancient glow one more time. The afterglow of the Big Bang carries tiny ripples, slight variations in temperature from point to point across the sky. These ripples are the seeds of everything. Every galaxy, every cluster, every void in the cosmic web grew from these faint imprints. And for the most part, they behave exactly as predicted, smooth, random, following a pattern called Gaussian noise. But not entirely. There are features like the cold spot that break the expected pattern. They're rare enough to be curious but persistent enough to be unsettling. If the early universe was as simple as our models suggest, these wrinkles shouldn't be there. Something may have happened in the universe's first moments that we haven't accounted for. And it's not just light that behaves strangely on the largest scales. Galaxy clusters are not sitting still. Across vast stretches of space, entire groups of galaxies appear to be streaming, drifting together in one direction, as if pulled by something enormous and unseen. One of these mysterious attractors sits hidden behind the plane of our own Milky Way. Scientists call it the Great Attractor. It has the gravitational influence of millions of billions of suns. And it's not alone. There are regions that seem to push galaxies away too, acting as cosmic repellers. These large-scale flows suggest that the distribution of mass in the universe is far stranger and more uneven than our models comfortably predict. So where does all of this lead? If dark energy continues doing what it's doing, and there is no sign that it will stop, then the future of the universe is a slow, silent isolation. Galaxies beyond our local group will drift further and further away, their light stretching into longer and longer wavelengths, until one by one, they cross a threshold and vanish from our observable sky. Not destroyed, just unreachable. Over trillions of years, the night sky will empty. The universe will still be there, but most of it will be forever beyond our horizon. That is one possible ending. But no one knows whether dark energy will stay constant, grow stronger, or someday reverse. The ultimate fate of everything is still an open question. Now, most black holes we know about were born from dying stars. Massive stars that burned through their fuel, collapsed under their own weight, and punched a hole in space-time. But there may be others, black holes that were never stars at all. Some theories suggest that in the first fractions of a second after the Big Bang, when the universe was unimaginably hot and dense, tiny pockets of matter could have been squeezed so tightly that they collapsed into black holes right then and there. Primordial black holes. If they exist, they've been drifting invisibly through galaxies for nearly 14 billion years. Some physicists have even wondered whether these ancient, unseen relics might account for part of dark matter itself. A universe full of invisible black holes, older than any star that ever shone. And speaking of black holes that shouldn't be there, astronomers have a problem at the other end of the scale. They've found quasars, blazing cores of distant galaxies powered by supermassive black holes, that existed when the universe was less than 1 billion years old. These black holes weigh 1 billion times more than our sun. And the problem is simple. There wasn't enough time. 1 billion years is not long enough by any standard model for a black hole to eat its way to that size. Not even close. So either they formed through some process we haven't imagined yet, or they were born massive from the very beginning. Either way, something about our understanding of how black holes grow is wrong. Let's leave the massive for a moment and think about the lost. Not every planet has a home. Somewhere between the stars, in the cold and the dark, there are planets drifting alone. No sun to orbit, no warmth to receive, just frozen worlds, moving silently through interstellar space. They may have been ejected from young solar systems during violent gravitational encounters, flung outward with enough force to never return. And here's what makes it strange. Some estimates suggest these rogue planets may actually outnumber planets with stars. Billions of them, maybe more, wandering the galaxy in total darkness. An invisible population of worlds, and we've barely begun to count them. Now imagine a galaxy. You probably picture something bright. A dense core, sweeping spiral arms, billions of stars packed together. But there are galaxies that look almost nothing like that. Astronomers call them ultra-diffuse galaxies, and they are enormous but incredibly faint. Their stars are scattered so thinly they look like dying embers spread across a dark floor. Some of these ghost galaxies appear to contain almost no dark matter at all, which shouldn't be possible. Others seem to be almost entirely dark matter with barely any visible stars. They contradict each other, and they both contradict our best theories of how galaxies are supposed to form. Something even stranger emerges when you look at quasars across vast distances. Quasars are among the brightest objects in the universe. Supermassive black holes devouring matter at the centers of galaxies, blazing with light. Each one formed independently, separated by billions of light years, with no physical connection to the others. And yet, in certain regions of the sky, their spin axes appear to be aligned, pointing in the same direction, as if some large-scale structure or force or condition in the early universe, nudged them into agreement across distances so vast that no signal could have traveled between them. No one can explain it, and no one expected it. Closer to home, there's a different kind of mystery. When scientists run simulations of how galaxies like our Milky Way should form, the models predict hundreds, sometimes thousands, of small satellite galaxies buzzing around the main one. But when we look at the real Milky Way, we find far fewer. The ones that should be the most visible, the most massive, the ones too big to fail, are either missing or strangely dim. This is called the missing satellite problem, and it has haunted cosmology for years. Either our simulations are wrong, or dark matter behaves in ways we haven't figured out yet, or these galaxies are out there and somehow hiding in plain sight. Every now and then, a particle strikes Earth's atmosphere with energy that defies belief. A single subatomic particle no larger than the nucleus of an atom, carrying the kinetic energy of a baseball thrown at full speed. These are ultra-high-energy cosmic rays, and they are the most energetic particles ever detected, far beyond anything the most powerful human-built accelerators can produce. And yet we don't know where they come from. Their paths are bent by magnetic fields as they cross the cosmos, so by the time they reach us, any trace of their origin has been scrambled. Something out there is accelerating particles to almost the speed of light. Something enormous, something violent, and it remains unnamed. Here's a quieter mystery, but one that keeps cosmologists up at night. After the Big Bang, the universe cooked up the lightest elements, hydrogen, helium, and a small amount of lithium. The recipes are well understood, the physics is solid, and the predicted amounts of hydrogen and helium match observations beautifully. But lithium doesn't. When astronomers look at the oldest stars in the galaxy, stars that formed from nearly pristine Big Bang material, they find roughly 3 times less lithium than the models say should be there. It's a small element, a small discrepancy, but it's stubbornly persistent, and after decades of searching, no one has found a convincing explanation. Something in our understanding of the early universe, or of how old stars process their material, is incomplete. And then there are the stars that seem almost too old to exist. A few ancient star clusters and a handful of individual stars have estimated ages that push right up against the age of the universe itself. Within the margins of error, some appear to be almost 14 billion years old, nearly as old as everything. This creates an uncomfortable tension. If these stars ignited that early, it means the very first generation of stars formed faster than most models predict. It pushes our timeline of cosmic dawn to its limits. And if any measurement shifted just slightly, we'd have stars older than the universe that contains them. Which, of course, is impossible. Probably. And finally, the silence. This one isn't about light or matter or energy. It's about what's missing. Our galaxy alone contains hundreds of billions of stars. Many of them have planets. Many of those planets sit in zones where liquid water could exist. Multiply that by the hundreds of billions of galaxies in the observable universe, and the numbers become staggering. If life arises even rarely, the cosmos should be full of civilizations. Some of them millions of years older than ours. Some of them presumably building things we could detect, radio signals, megastructures, waste heat from vast technologies. And yet, every survey, every search, every scan of the sky has returned the same answer. Silence. No signal. No sign. The physicist Enrico Fermi asked the question simply, where is everybody? And after more than 70 years, we still don't have an answer. The universe is very, very large. And so far, it is very, very quiet. If you zoom out far enough, further than galaxies, further than galaxy clusters, a pattern appears. Matter in the universe is not scattered randomly. It's arranged into long, delicate filaments, like threads of silk connecting dense knots of galaxies. Between these threads are enormous voids, bubbles of near emptiness millions of light years across. Together, it all forms a structure that looks eerily like a three-dimensional spiderweb, the cosmic web. And here's what's remarkable. This web was seeded by quantum fluctuations. Tiny, random jitters in the fabric of reality during the first instant of the universe, smaller than an atom, somehow grew over billions of years into the largest structures that exist. We can simulate it. We can map parts of it. But exactly how those infinitesimal ripples sculpted something so vast and so graceful is still not fully understood. Now, sometimes the universe doesn't whisper. Sometimes it screams with light. A gamma ray burst is the single most violent event known to occur in the cosmos. For a few seconds, sometimes less, A narrow beam of energy erupts with such intensity that it outshines the entire galaxy it lives in. Every star, every nebula, every other source of light in a galaxy of hundreds of billions of stars, temporarily eclipsed by one event. Some are born from the collapse of massive stars. Others seem to come from neutron stars spiraling into each other and merging. But the precise chain of events, how the energy is focused into such a tight beam, how it reaches such extremes, is still not entirely clear. For a few blinding seconds, one point in the universe becomes the brightest thing in existence. And then it's gone. There are galaxies that hide, not behind anything physical you'd recognize, but behind dust. Thick, dense shrouds of cosmic dust that block visible light almost entirely. If you looked at these galaxies with your eyes, you'd see almost nothing. But point an infrared telescope at them and they blaze. Ultraluminous infrared galaxies, they're called. Some of them are hundreds of times brighter than the Milky Way, but all of that brightness is trapped and re-emitted in infrared by the dust surrounding them. Something extraordinary is happening inside. Either an explosion of star formation unlike anything in our galaxy, or a supermassive black hole feeding violently at the center, or both at once. Astronomers have debated for decades which explanation is correct. The answer might be that it depends on the galaxy, but the dust keeps its secrets well. In 2019, astronomers found something no one was looking for. Enormous, faint rings in radio wavelengths, hanging in space far outside any galaxy. They were huge, some wider than 1,000,000 light-years across and perfectly circular. They didn't match any known object or phenomenon. They were called odd radio circles, which is the kind of name scientists give something when they genuinely have no idea what it is. Some theories suggest they could be massive shock waves from events in distant galaxies, perhaps the aftermath of a merger between two supermassive black holes. Others think they might be outflows or energy bubbles from galactic centers. But none of these ideas fit perfectly. The circles are still there, still unexplained, still odd. Look back far enough in time and the universe shows you galaxies that shouldn't quite make sense. In the early cosmos, astronomers have found galaxies that are extraordinarily massive, packed with stars and matter, yet physically tiny. Dense in a way that galaxies today simply aren't. Imagine something with the mass of a large modern galaxy compressed into a volume 10 times smaller. How did so much material come together so tightly, so quickly, when the universe was still young? And if these compact, ultramassive galaxies existed then, where did they go? The best guess is that they gradually puffed up over billions of years through mergers and collisions, eventually becoming the larger, more spread-out galaxies we see around us today. But the details of that transformation are still being worked out. Here's a mystery that's almost embarrassing for cosmology. We know, with great precision, how much ordinary matter the universe should contain. Protons, neutrons, electrons, the stuff that makes up stars, planets, people. The number comes from measurements of the Big Bang's afterglow and from observations of how light elements formed in the early universe. And when we add up all the ordinary matter we can see, in stars, in galaxies, in glowing gas clouds, it's not enough. Roughly half of it is missing. Not dark matter, ordinary matter, the kind we understand perfectly well. It took decades, but astronomers have started finding some of it hiding in faint, hot filaments of gas stretching between galaxies, almost invisible, spread so thin it barely registers. But whether we've found all of it yet is still an open question. Deep inside massive galaxy clusters, radio telescopes have revealed something delicate and strange. Thread-like structures, long and impossibly thin, glowing faintly in radio wavelengths. They look like the remnants of something ancient, old shock waves, perhaps, or the trails of turbulence from galaxies plowing through the thin gas that fills the space between them. Scientists call them radio relics. Some stretch for millions of light years. What makes them puzzling is their persistence. The energy that lights them up should have faded long ago. Something is keeping these ghostly filaments alive, re-energizing them across cosmic timescales, and no one is entirely sure what. Not all galaxies are symmetrical. You might expect them to be. Gravity pulls evenly in all directions, after all. But many galaxies are visibly lopsided. One spiral arm longer than the other. One side brighter, more extended, more disturbed. Some of these asymmetries come from collisions, a nearby galaxy passing too close and pulling things out of shape. Others might be caused by uneven clumps of dark matter tugging from within. And some galaxies appear lopsided for no obvious reason at all. No nearby intruder, no recent merger, just a quiet galaxy sitting slightly off balance, as if something nudged it long ago and it never quite settled back. After the Big Bang, the universe cooled. The first atoms formed, mostly hydrogen, and for a long time there were no stars, no galaxies, no light. This period is sometimes called the cosmic dark ages. Then, slowly, the first stars ignited. Their ultraviolet light began stripping electrons off the surrounding hydrogen gas, making it transparent again. This process is called reionization, the moment the universe lit up for good. But when exactly did it happen? And how long did it take? Was it a sudden dawn, or a slow, patchy brightening that took hundreds of millions of years? Different observations point in slightly different directions. The James Webb Space Telescope is pushing further back than ever before, finding galaxies at the very edge of this transition. But pinning down the exact timeline of how the universe woke up remains one of cosmology's great open investigations. And now, perhaps the deepest question of all. What shape is the universe? Not the shape of what's inside it, not the spirals of galaxies or the web of filaments, but the shape of space itself. Every measurement we've made suggests that space is very close to flat. Not curved like a sphere, not saddle-shaped, but flat, stretching outward in every direction. But very close to flat is not the same as perfectly flat. And even if it is flat, that doesn't tell us whether it goes on forever or whether it eventually wraps back around on itself in some way we can't perceive. The observable universe has an edge, not a wall, but a horizon beyond which light hasn't had time to reach us. What lies beyond it? More of the same? Something different? An end? There may be no way to know. The universe might be infinite. It might be finite but unbounded, like the surface of a sphere with no edge. And it is entirely possible that this is a question the cosmos will never let us answer. Now imagine a black hole, but in reverse. General relativity, Einstein's masterwork, doesn't just predict black holes. Hidden in the same equations is something else. A mirror image, a region of space-time where nothing can fall in and matter only flows out. Physicists call them white holes. Mathematically, they're perfectly valid. The equations allow them, but no one has ever seen one. Not a single confirmed detection in any wavelength at any distance. They may be real objects waiting to be found, or they may be ghosts, solutions that exist only on paper, artifacts of math that the universe chose not to build. We don't know which. And until we find one or prove they're impossible, white holes remain one of the strangest predictions physics has ever made. And speaking of things we can't quite explain, the beginning of the universe appears to have cheated once. Very early on, within the tiniest fraction of a second after the Big Bang, space itself seems to have expanded faster than light. Not objects moving through space, but space itself stretching, inflating at a staggering rate, smoothing out every wrinkle, every irregularity, flattening the cosmos into the nearly uniform expanse we see today. This is called inflation, and the evidence for it is strong. But here's what we don't know: what started it. What field, what mechanism, what trigger caused the universe to suddenly inflate? And then, just as mysteriously, to stop. Something turned it on. Something turned it off. And that something has no confirmed identity. Let's come closer. Not to the edge of the universe, but to the skies of other worlds. In the last few decades, we've learned to read the atmospheres of planets orbiting distant stars. Light from their host star passes through the thin shell of gas surrounding the planet, and by studying what wavelengths are absorbed, we can identify molecules: water, methane, carbon dioxide. But some exoplanets return spectra that don't make sense. The chemical signatures don't match what models predict for their temperature, their size, their distance from their star. Something in those alien skies, some process, some chemistry, some atmospheric behavior, is happening that we don't yet have a framework to explain. And some of those alien worlds have a different kind of problem. They're too big, not too massive, too physically large. Certain hot Jupiters, gas giants orbiting dangerously close to their stars, are puffed up to sizes that their mass alone cannot justify. Even accounting for the intense heat pouring in from their nearby star, they're still bigger than they should be. Something inside them is generating extra energy, or preventing them from contracting, or inflating them through a mechanism we haven't identified. They float there, bloated and inexplicable, like balloons that refuse to deflate. Now here is a thought that can make the ground feel less solid beneath you. We treat the constants of physics, the speed of light, the strength of gravity, the fine structure constant that governs how charged particles interact, as fixed, unchanging, the same everywhere, always. But a few careful measurements, taken across vast distances and deep time, have hinted that this might not be entirely true. Some observations suggest that the fine structure constant may vary ever so slightly, depending on where you look in the cosmos or how far back in time you peer. If this is real, and it is still a very large if, it would mean that the basic rules of physics are not universal, that the laws themselves shift softly across space and time. It's one of those ideas that most physicists approach with extreme caution, because if it's true, almost everything gets more complicated. Where does gold come from? Not from the earth merely inherited it. Gold, platinum, uranium, and many of the heaviest elements in the periodic table are thought to be forged in some of the most violent events the universe produces. When two neutron stars spiral into each other and merge, the collision is so extreme that it fuses atomic nuclei into heavy elements and scatters them across space. We've even detected the gravitational waves from such a merger and seen the afterglow rich with heavy elements. But here's the problem: neutron star mergers alone may not produce enough. The numbers don't quite add up. There may be other cosmic factories involved, certain types of supernovae, or collisions we haven't considered. The recipe for the heaviest elements in your body is still being written. Every now and then, a radio telescope captures something that doesn't fit any known category. An object appears in the data, shining in radio wavelengths, persisting for months, sometimes years, and then fading into nothing. No counterpart in visible light. No X-ray signature. No match to any cataloged star, galaxy, or known phenomenon. These are called long-lived radio transients, and they are genuinely mysterious. Some might be exotic stellar remnants, dead stars behaving in unexpected ways. Others could be jets of energy from distant black holes, seen from an unusual angle. Or they could be something else entirely, something we haven't thought of yet. They appear, they glow, they vanish, and we are left staring at the empty patch of sky where they used to be. Here's a subtle one. When astronomers map the spin directions of spiral galaxies across large areas of the sky, something curious appears. There might be a slight imbalance. A few more galaxies spinning one way than the other. Now, in a perfectly symmetric universe, one that has no preferred direction, no built-in handedness, you'd expect an even split. clockwise and counterclockwise, perfectly balanced over large enough samples. But some studies have found a small, nagging asymmetry. It's not dramatic. It could be a statistical fluke or a bias in how we observe. But if it's real, it would suggest that the universe has a subtle preference. A cosmic handedness that standard cosmology does not predict and cannot easily explain. Some planetary systems look like they've been through a war. In our solar system, the planets orbit in roughly the same plane, aligned with the sun's equator, all spinning in more or less the same direction. It's orderly, predictable, but out there, astronomers have found systems where planets orbit at wild angles, sharply tilted, sometimes nearly perpendicular to their star's rotation. Some even orbit backwards. These misalignments tell a story of violence, gravitational encounters with passing stars, planets that migrated inward and were yanked off course, unseen companions whose gravity warped the entire system over millions of years. Each tilted orbit is a scar from a chaotic past that we can only partially reconstruct. Right now, all around you, passing through your body, through the walls, through the Earth itself, there is a sea of neutrinos left over from the Big Bang. Not the neutrinos from the sun or from supernovae, but ancient ones, released when the universe was about 1 second old. They are called the cosmic neutrino background, and they are the oldest particles in existence. We know they're there. The math demands it, and we have indirect evidence from the way the universe expanded. But we have never directly detected them. They are so low in energy, so ghostly, so reluctant to interact with anything, that no instrument we've ever built can catch them. An entire ocean of primordial particles, filling every cubic centimeter of space, and we can only infer their presence from shadows in the data. Some galaxies can't seem to make up their minds. Active galaxies, those with bright, quasar-like cores powered by supermassive black holes devouring matter, are supposed to change slowly. Over millions of years, not decades. But a handful of these galaxies have done something startling. They've switched off, or switched on. Their brilliant cores fading to almost nothing over just a few years, or flaring to life from what seemed like a quiet, ordinary galaxy. These are called changing-look active galaxies, and they challenge everything we thought we understood about how black holes feed. The fuel supply shouldn't change that fast. The disk of matter spiraling inward shouldn't just vanish. And yet it does, as if someone flipped a switch on one of the most powerful engines in the universe. In a few rare cases, astronomers have looked at what appears to be a single quasar and found two twin blazing cores, close together, each powered by its own supermassive black hole. These are binary supermassive black holes, two monsters orbiting each other at the centers of merging galaxies. They're expected to exist. When galaxies collide, their central black holes should eventually find each other and spiral inward. But eventually is the problem. The physics predicts that getting two supermassive black holes to actually merge is surprisingly difficult. They can stall, orbiting each other for billions of years, unable to shed enough energy to close the final gap. This is called the final parsec problem. And some of these pairs seem to be stuck in exactly that limbo. We know about small black holes, the ones left behind when massive stars die, a few times the mass of the sun. And we know about the giants, supermassive black holes, millions or billions of solar masses, sitting at the centers of galaxies. But between those two extremes, there's a gap. Intermediate mass black holes, in the range of hundreds to thousands of solar masses, should exist. Logic says they must. They could be the seeds that grew into supermassive black holes, or the products of dense star clusters merging together. But confirmed detections are vanishingly rare. Either they are genuinely scarce, or they are hiding in environments where they produce little light or radiation. A missing middle chapter in the story of black holes. Millisecond pulsars are the most precise natural clocks in the universe. Neutron stars, spinning hundreds of times per second, sweeping beams of radio waves with a regularity that rivals atomic clocks. Astronomers use them to detect the faintest disturbances in space-time. A passing gravitational wave, an unseen planet tugging gently on the pulsar, a distant black hole warping the fabric of space between us and the signal. But some of the timing irregularities don't match any known source. Tiny, persistent deviations that hint at something hidden. Maybe undiscovered companions. Maybe a background hum of gravitational waves from merging black holes all across the universe. Or maybe something we haven't imagined yet, whispering through the timing data, just below the threshold of understanding. Saturn's rings look simple from a distance. A smooth, flat disk of ice and rock circling the planet. But look closer and they are anything but simple. The rings have gaps so sharp they look cut with a blade. Edges so crisp they seem impossible for a structure made of billions of tumbling particles. Tiny moons embedded within the rings sculpt narrow lanes and create waves. Gravitational resonances with larger moons carve out broader divisions. And some features, kinks, braids, ripples, still can't be fully accounted for. The rings are a gravitational orchestra, and we can hear the music, but some of the instruments remain unidentified. Scattered through our galaxy are a few stars that seem almost impossibly old and almost impossibly pure. Stars with nearly no heavy elements at all, no carbon, no oxygen, no iron to speak of. Just hydrogen and helium, and traces of the lightest elements cooked up in the Big Bang. These ultrametal-poor stars are fossils. They formed from gas that had been barely touched by previous generations of stars. Some of them may have been born in the very first wave of star formation, when the universe was still young and chemically pristine. Studying them is like reading a letter written in the universe's infancy. But the text is faded, and we are still learning how to read it. Remember the cold spot in the cosmic microwave background, that strange, unexplained patch of slightly colder temperatures in the ancient light of the Big Bang. It's not the only oddity. When scientists analyze the largest patterns in the microwave sky, they find alignments that shouldn't be there. The lowest frequency temperature patterns, the ones that stretch across the entire sky, seem to line up with each other, and even with the plane of our solar system, in ways that standard cosmology cannot explain. This coincidence has been nicknamed the axis of evil, and it has frustrated cosmologists for years. Is it a statistical fluke, the kind of thing that happens by chance in a universe this large? A subtle error in the way we process the data? Or a genuine clue that something about our understanding of the universe's largest structures is wrong? Some galaxies burn brightly in X-rays but look completely ordinary when you photograph them in visible light. This is a contradiction. X-ray emission at that intensity usually means something violent is happening. A supermassive black hole actively feeding, or vast clouds of superheated gas. But the visible light says otherwise. It says this is a normal, quiet galaxy with nothing unusual going on. These X-ray bright, optically dull galaxies may harbor deeply buried black holes, shrouded in so much dust and gas that their visible light is almost entirely blocked. Or they may contain exotic structures of hot gas that we don't fully understand. Either way, the X-rays are telling us one story and the visible light is telling another. And somewhere between the two lies the truth. Our neighborhood in the cosmos is a little emptier than it should be. The Milky Way sits near the edge of what astronomers call a local void, a region of space where galaxies are noticeably scarcer than average. It's not dramatic. It's not a hole in the universe, but it is a measurable underdensity, and it may have subtle consequences. Some researchers have wondered whether living near this void slightly biases our measurements of the universe's expansion, making things appear to accelerate in ways that might partially mimic dark energy. Most cosmologists think the effect is too small to matter, but the question lingers. We measure the universe from a particular spot, and that spot may not be as typical as we'd like to believe. And finally, in this stretch of mysteries, a handful of gamma-ray bursts have broken one of the cleanest rules in astrophysics. Long gamma-ray bursts, the kind that last more than 2 seconds, are supposed to come from the deaths of massive stars. A huge star collapses, its core implodes, and a jet of gamma rays erupts. And in almost every case, a bright supernova follows within days. The explosion that accompanies the collapse. But a few long gamma-ray bursts have shown no supernova at all. The jet appeared, the afterglow faded, and no explosion followed. These orphan bursts challenge the simple narrative. If the star didn't explode, what happened to it? Did it collapse directly into a black hole without the usual fireworks? Or is there a completely different mechanism at work, one that can produce the universe's most powerful explosion, without the explosion we expected to come with it? There are galaxies out there with almost nothing to see, not because they're far away, but because they barely have any stars. Astronomers have detected galaxy-sized clumps of dark matter, massive enough to hold a galaxy together, sitting in space with only a handful of stars, or none at all. Dark galaxies. The raw material was there. The gravitational pull was there. Everything needed to ignite a galaxy full of stars was in place. But something didn't happen. The gas never condensed, or it was blown away too early, or some process we don't understand prevented the stars from forming. These invisible structures may be scattered throughout the universe in numbers we can't yet estimate. Galaxies that were supposed to light up and never did. And this connects to one of the deepest puzzles in black hole science. We know that supermassive black holes exist at the centers of nearly every large galaxy. We've seen them blazing as quasars in the very early universe, already billions of times the mass of the Sun when the cosmos was barely 1 billion years old. But what were they before they were massive? Every giant starts as something small, and we don't know what that something was. Some theories suggest enormous clouds of primordial gas that collapsed directly into black holes without ever becoming stars. Others propose dense clusters of early stars that merged together rapidly. And some point back to those primordial black holes we mentioned earlier, relics of the Big Bang itself that served as seeds. The truth might be different for different black holes. But the identity of the very first seeds remains one of the oldest unsolved questions in astrophysics. In 2015, a star called KIC 8462852, quickly nicknamed Tabby's star, did something no one could explain. Its brightness dropped, not in the smooth, predictable way a planet causes when it passes in front of its star. This was irregular, asymmetric, and deep. Some dips blocked up to 20% of the star's light, which is far too much for any planet. Ideas ranged from swarms of shattered comets to vast clouds of dust to, for a brief electric moment, the possibility of alien megastructures. The megastructure idea didn't hold up, but neither did any single natural explanation. And Tabby's star isn't alone. A handful of other stars have since shown similar bizarre, irregular dimming patterns, each one slightly different, each one resisting a clean answer. Something is passing in front of these stars, and in some cases we still don't know what. Between the galaxies in a massive cluster, there is a glow, not coming from any galaxy, not coming from any star you can point to, just a faint, diffuse light spread across the dark spaces between galaxies like mist between trees. This is intracluster light, and it comes from orphan stars, stars that were ripped from their home galaxies by gravitational interactions, flung into the void, and left to drift alone. Billions of them scattered throughout the cluster, belonging to nothing. The light they produce is incredibly faint, but it's real, and when you add it all up, it can account for a significant fraction of the cluster's total starlight. What's debated is exactly how these stars were orphaned. Tidal stripping during galaxy mergers? violent encounters that ejected them, a slow, steady process, or sudden catastrophic events. The orphan light glows softly, and the full story of how it got there is still being assembled. The atmospheres of some exoplanets read like a recipe that shouldn't exist. When astronomers break down the light passing through a distant planet's atmosphere, they expect to find elements in ratios that reflect where and how the planet formed. Planets born close to their stars should have one chemical fingerprint. Planets born far out in the cold should have another. But some exoplanets show ratios of carbon to oxygen or metal abundances that don't match any simple formation story. They have too much of one thing, too little of another, as if they were assembled from materials gathered in wildly different parts of their solar system. This suggests migration, planets that formed in one place and drifted to another, collecting different chemical layers along the way. But tracing exactly which journey produced which atmosphere is a puzzle we're only beginning to untangle. Some quasars don't just consume, they also expel. At speeds that defy intuition, 10, 20, sometimes 30% the speed of light, vast outflows of gas are launched from the regions around supermassive black holes. These ultra-fast outflows carry enough energy to reshape entire galaxies. They can sweep through the surrounding gas, shutting down star formation, heating the intergalactic medium, and fundamentally altering the galaxy's future. But how? How does a black hole, whose defining feature is pulling things in, manage to fling material outward at a significant fraction of light speed? Radiation pressure, magnetic fields, and the extreme physics of accretion disks all play a role. But the precise mechanism, the exact choreography that turns infalling matter into an outward blasting wind, is still not fully understood. Between the heaviest neutron stars and the lightest black holes, there is a gap. Neutron stars seem to max out at around 2 to 2.5 times the mass of the Sun. The lightest known black holes start at around 5 solar masses. And in between, in that range of roughly 2.5 to 5 solar masses, there is almost nothing. This is called the mass gap, and for years, astronomers debated whether it was real or just an artifact of how we detect these objects. Recent gravitational wave detections have found a few objects that might fall in this range, blurring the boundary. But the question remains, is there a physical reason why collapsing stars skip over these masses? Does the explosion that creates a neutron star or a black hole somehow prevent objects from landing in this middle zone? Or are they out there, quietly hiding, waiting to be found? Even when you subtract every known galaxy, every star, every identified source of light in the universe, there is still a glow, a faint, diffuse background of light that fills the sky in every direction. It's called the extragalactic background light, and it has been measured carefully, and it is slightly brighter than it should be. If you add up all the light from every galaxy we can see, there's still something left over. Where does the extra light come from? Some of it may be from galaxies too faint and too distant to detect individually, billions of tiny ancient galaxies just below our detection threshold. Some might come from stars stripped from galaxies and drifting in intergalactic space. And more exotic ideas suggest decaying dark matter particles or other unknown processes could contribute. The sky is never truly dark, and we don't fully know why. Every now and then, a star goes rogue, not drifting slowly like a wandering planet, but streaking through space at extraordinary speed, fast enough to escape the galaxy entirely. These hypervelocity stars move at thousands of kilometers per second, far faster than anything their local environment can explain. The leading theory is dramatic. A binary star system, two stars orbiting each other, wanders too close to the supermassive black hole at the center of the galaxy. One star is captured. The other is flung outward at tremendous speed, like a stone from a slingshot. The physics works, and we've traced some of these stars back toward the galactic center. But not all of them. Some hypervelocity stars seem to come from directions that don't point back to any known black hole. Something else launched them, and whatever it was powerful enough to throw a star out of an entire galaxy. And finally, the question that may matter more than any other in this list. Is our planet's atmosphere common, or is it a freak accident? We know Earth has a nitrogen-oxygen atmosphere held in place by a magnetic field, warmed by a stable star, with liquid water on the surface and a chemistry that supports life. And we have begun, just barely, to probe the atmospheres of small, rocky exoplanets orbiting other stars. The James Webb Space Telescope has started to return data, but the sample is tiny, a handful of worlds, and so far the results are ambiguous. Some rocky planets appear to have atmospheres, others may not. Whether Earth-like conditions, breathable air, temperate climates, the quiet chemical balance that allows biology, are scattered across the galaxy or vanishingly rare is one of the biggest unanswered questions in all of science. We are searching for mirrors, and we don't yet know if the cosmos has any. Picture a star drifting through the quiet outskirts of a galaxy. It has orbited peacefully for billions of years, but this time its path curves just a little too close to the center. Too close to the supermassive black hole that sits there, patient and invisible. And the star doesn't stand a chance. The black hole's gravity grabs one side of the star more strongly than the other, and the difference is enough to tear it apart. Not in an explosion, in a long, slow unraveling. The star stretches into a thin ribbon of superheated gas that spirals inward, brightening into a flare that can outshine the entire galaxy. These are called tidal disruption events. We've observed dozens of them now, but when astronomers compare the way the light brightens, flickers, and fades to what the models predict, the match isn't clean. The flares are messier, more variable, more surprising than the theory says they should be. The star is destroyed. The light tells a story, and we can't quite read all of it yet. Something is blinking in the radio sky, and it's blinking too slowly. Pulsars, spinning neutron stars that sweep beams of radio waves like lighthouses, typically pulse many times per second, or at most once every few seconds. But a handful of objects have been found that pulse on timescales of minutes, even hours. Long, slow, regular blinks of radio energy, separated by silences that no known type of neutron star or magnetar should produce. They've been called ultra-long period radio transients, and they don't fit neatly into any existing category. A neutron star spinning that slowly should have lost the ability to produce radio emission long ago. A magnetar might explain the energy, but not the timing. Something is out there, pulsing patiently in the dark, and we don't know what kind of object it is. When a star like our sun dies, it doesn't explode. It swells into a red giant, sheds its outer layers, and leaves behind a small, hot core surrounded by an expanding cloud of glowing gas. This is a planetary nebula, and they are among the most beautiful objects in the universe. But they are also among the most puzzling, because the star that made them was round, roughly spherical, with no obvious reason to produce anything other than a spherical shell of gas. And yet, planetary nebulae come in hourglasses. Butterflies, rings, spirals, intricate, symmetric shapes that look almost designed. Something breaks the symmetry. It might be a companion star. It might be magnetic fields. It might be the way the star rotated as it died. But despite decades of study, no single explanation accounts for the full range of shapes we see. Simple stars are making complex art, and we don't fully understand how. Some galaxies are at war with themselves. From the outside, they look normal, a disk of stars rotating in one direction as expected. But look deeper and you find a second component, a ring of gas or a population of stars rotating the opposite way, counter-rotating, moving against the flow of the rest of the galaxy. This shouldn't happen in a galaxy that formed from a single collapsing cloud of gas. Everything should spin the same way, so something must have happened. A merger with another galaxy that was spinning differently. A stream of intergalactic gas falling in from an unexpected angle. Whatever the cause, these counter-rotating components are frozen records of a collision or encounter that the galaxy has absorbed but not fully digested. The scars are still turning. Before the first galaxies, before the first stars lit up the darkness, the universe was in its dark ages. And somewhere in that darkness, the first black holes were born. Not the supermassive giants we see later, those came after. These were the originals, the seeds, and we don't know what they were. One possibility is that the very first generation of stars hundreds of times more massive than our sun, burning hot and dying fast, collapsed directly into black holes. Another is that vast clouds of primordial gas, too massive to form a single star, collapsed wholesale into black holes without ever igniting. There are even more exotic proposals, but no telescope has yet seen the moment of first formation. The birth of the first black holes happened in the dark, and it remains there. Some planetary systems are packed so tightly they seem impossible. Planets orbiting close together, their orbital periods locked in near-perfect mathematical ratios. A gravitational ballet where each planet's motion is synchronized with its neighbors. These are called resonant chains, and some of them are astonishingly delicate. The TRAPPIST-1 system, for instance, has 7 Earth-sized planets packed into an area smaller than the orbit of Mercury, each one tugging on the others in a precise, interlocking rhythm. It looks fragile. It looks like it should have fallen apart long ago, and yet it hasn't. Meanwhile, other systems that started in similar configurations did fall apart, their planets scattering, colliding, or being ejected. What decides which knife-edge arrangements survive and which ones crumble? The answer depends on initial conditions so subtle that we can barely measure them. Order and chaos, separated by a hair's width. Look at many spiral galaxies and you'll see something cutting through the center. A bright, straight bar of stars, slicing across the disk like a beam of light through fog. These galactic bars are common. Our own Milky Way has one, and they aren't just decorative. They funnel gas toward the center of the galaxy, trigger new star formation, and reshape the entire structure over time. But what creates them? The basic answer is gravitational instability. The disk becomes unstable and matter organizes into a bar shape. But the details matter, and the details are messy. What determines when a bar forms? What decides how long it lasts? Why do some galaxies have strong bars while others, seemingly similar, have none at all? The bar is one of the most prominent features a galaxy can have, and the precise recipe that builds one is still under active investigation. Not all stellar explosions follow the script. A typical supernova has a well-understood brightness, so well understood, in fact, that certain types are used as measuring sticks for the entire universe. But some supernovae are too bright, dramatically, absurdly too bright, 10, 50, sometimes 100 times more luminous than they should be. These superluminous supernovae seem to require an extra engine. Maybe a rapidly spinning magnetar at the center, pouring energy into the expanding debris. Maybe the shock wave slamming into dense surrounding gas. The explanations work in some cases, but not all. And then there are the other outliers, supernovae that are strangely faint. Quiet, dim explosions that barely register, as if the star couldn't quite commit to dying. The range of stellar death is wider, stranger, and more diverse than any single theory can comfortably contain. Somewhere between the galaxies, drifting through the vast emptiness of intergalactic space, there may be black holes that belong to nothing. Simulations of galaxy mergers show that when two supermassive black holes meet, gravitational wave recoil can kick one of them out of the newly merged galaxy entirely. flung into the void at thousands of kilometers per second, never to return. These ejected black holes would be nearly impossible to detect. No accretion disk, no glowing gas, no stars to betray their presence. Just a dark, massive object moving silently through the space between galaxy clusters. We don't know how many there are. We don't know if we've ever seen one, but the simulations insist they should exist, solitary giants, exiled from their homes, wandering the darkest spaces in the universe. Even our own solar system holds a secret about the future that no one can fully predict. The orbits of the planets look stable. They've been stable for billions of years. But mathematically, the solar system is chaotic. Not in a dramatic, obvious way. The planets won't suddenly go flying in random directions. But tiny gravitational nudges between planets accumulate over time, and over billions of years, their effects become unpredictable. Simulations show that in some scenarios, Mercury's orbit could become unstable, eventually crossing paths with Venus. In others, Mars gets nudged just enough to disrupt the inner solar system entirely. The probability is small, but it's not zero, and this is just our system with only 8 planets. Systems with 3, 4, 5 closely packed worlds face the same tension between order and chaos amplified. Some architectures dance gracefully for billions of years. Others, nearly identical, tear themselves apart. And predicting which is which remains one of the deepest unsolved problems in celestial mechanics. And then there are the rings. Not planetary rings, galactic ones. Some galaxies are wrapped in faint arcs and rings of stars, encircling them like frozen ripples in a pond. These structures are enormous, stretching tens of thousands of light years, and they are old. They are the ghosts of collisions, the remnants of smaller galaxies that pass through or near a larger one, sending gravitational waves rippling through its disk of stars. The collision itself may have happened hundreds of millions of years ago, but the ring is still there, still expanding, still glowing faintly. Reconstructing exactly what happened, the angle of approach, the mass of the intruder, the speed of the impact, is like studying the ripples in a lake and trying to describe the stone that was thrown. We can see the aftermath, but the exact cosmic accident that caused it is still mostly guesswork. Some galaxies don't just have a bright core. They have arms, radio arms, stretching out into intergalactic space, far beyond the visible galaxy itself. These are giant radio galaxies, and their lobes of radio-emitting plasma can extend for millions of light years, dwarfing the galaxy that created them. The engine is always the same: a supermassive black hole at the center, launching jets of material outward at near-light speed. But the mystery is selectivity. Most black holes don't do this. Most galaxies with active cores produce jets that stay relatively contained. Only a rare few grow these enormous structures, inflating lobes that stretch across distances larger than the gaps between galaxies. What makes one black hole modest and another extravagant? The answer likely involves the black hole spin, the density of the surrounding environment, and perhaps the history of how it was fed. But the full recipe for building a radio galaxy that spans millions of light years is still being written. We talked earlier about the mass gap, the puzzling scarcity of objects between the heaviest neutron stars and the lightest black holes. But there's a related mystery at the very bottom of the black hole scale. When massive stars explode, theory predicts they should leave behind a range of black holes, including many just barely above neutron star mass, small, lightweight black holes, perhaps 3 or 4 times the mass of the Sun. But we don't see as many as we should. The population of tiny black holes is thinner than expected. Either something about the way massive stars die prevents these low-mass black holes from forming, or they form but are somehow hidden from our detection methods. The deaths of stars are among the most studied events in astrophysics, and yet the leftovers still surprise us. If you could see the Milky Way from the outside, edge on, you might notice something odd. The outer edges of the disk aren't flat. They curve. They warp, bending gently upward on one side and downward on the other, like a vinyl record left too long in the sun. And our galaxy isn't alone. Many spiral galaxies show similar warps in their outer regions. Something is pulling or pushing the edges out of alignment. It might be the gravitational influence of a nearby companion galaxy. It might be the shape of the dark matter halo surrounding the disk. It might be gas falling in from intergalactic space at an angle. The truth probably varies from galaxy to galaxy, but the warps are there, graceful and persistent, bending the edges of galaxies into shapes that a simple spinning disk should never make. And then there are the galaxies that seem to have been assembled at right angles. Polar ring galaxies have a normal-looking disk of stars at their center, and then a second structure, a ring of gas and stars orbiting perpendicular to it, straight through the poles like a halo turned on its side. The geometry is striking and strange. The most common explanation is a past encounter. A smaller galaxy was captured and its material was stretched into a ring that settled into a polar orbit. But how that ring remains stable over billions of years, without being pulled back into alignment with the main disk, is harder to explain. These galaxies are rare. Each one is a frozen record of an encounter that produced something that shouldn't quite work. And yet it does. In old star clusters, collections of stars that all formed at roughly the same time billions of years ago, most stars have aged predictably. They've reddened, dimmed, and settled into quiet late-life stages. But a few haven't. Scattered among the ancient population are stars that look too young, too bright, too blue. These are called blue stragglers, and they seem to have cheated time. The leading explanation is that they gained mass somehow, either by colliding and merging with another star, or by slowly siphoning material from a close companion. In either case, the extra mass reignited their furnaces, making them burn hotter and brighter, mimicking youth. But the exact pathways, which blue stragglers merged and which ones fed, differ from star to star and cluster to cluster. They are old stars wearing young faces, and each one has a slightly different disguise. At the hearts of massive galaxy clusters, the gas should be cooling. It's hot, tens of millions of degrees, and it radiates energy constantly in X-rays. As it loses energy, it should cool down, condense, and collapse into new stars. The math says this should happen rapidly, producing enormous amounts of star formation in cluster cores. But it doesn't. The centers of many galaxy clusters are surprisingly calm. Hot, but not cooling as fast as they should. Something is gently reheating the gas, keeping it from collapsing. The prime suspect is the supermassive black hole at the center of the cluster's largest galaxy, periodically injecting energy through jets and bubbles of hot plasma. But the balance is almost too perfect. Just enough energy to prevent cooling, but not so much that the gas is blown apart. How a chaotic, violent process like black hole feedback maintains such a delicate equilibrium is one of the most elegant and least understood phenomena in astrophysics. Some planets don't travel in circles. They don't even travel in gentle ellipses. Some exoplanets follow wildly elongated orbits, stretched, comet-like paths that bring them scorchingly close to their star at one end and fling them out into the cold at the other. The temperature swings on these worlds must be extraordinary. Seasons lasting not months but orbital periods, from extreme heat to deep cold and back again. How did they end up on such orbits? In most cases, something violent happened. A gravitational encounter with another planet. A close pass by a neighboring star. A history of migration and scattering that pumped energy into the orbit until it stretched into something that looks almost unstable. These eccentric worlds carry the memory of their chaotic past in every loop around their star. Between the galaxies in a cluster, the thin, hot gas that fills the space is not empty of structure. It is threaded with magnetic fields, vast, invisible lines of magnetic force winding through the intergalactic medium, stretching across millions of light years. We can detect them faintly through the way they polarize radio waves and bend the behavior of charged particles. But how did they get there? Magnetic fields don't just appear. They need to be generated, amplified, and spread. Some may have been seeded in the very early universe. Others may have been carried out of galaxies by outflows and explosions and then stretched and tangled by the motions of the cluster gas over billions of years. The universe is magnetic on scales we are only beginning to appreciate, and the origins of that magnetism remain deeply uncertain. Scattered through every galaxy are clouds of cold, dense molecular gas, the raw material from which stars are born. And many of them should be forming stars right now. They're dense enough, they're cold enough, all the conditions for gravitational collapse are met. And yet some of these clouds sit there, quiet and intact, for millions of years longer than they should. Something is holding them up. It might be turbulence, internal motions that stir the gas and prevent it from settling. It might be magnetic fields, providing an invisible scaffold that resists collapse. It might be feedback from nearby stars, sending gentle waves of energy through the cloud just often enough to keep it from tipping over the edge. These clouds have delay timers built in, and we don't fully understand who set them. A few nearby galaxies have presented astronomers with a genuinely uncomfortable observation. They seem to have far less dark matter than expected. In the standard picture, every galaxy is embedded in a massive halo of dark matter, an invisible cocoon that holds it together and shaped its formation. Dark matter is supposed to be non-negotiable, but a handful of small galaxies rotate in a way that suggests their dark matter content is minimal or possibly absent. If confirmed, this doesn't overturn the existence of dark matter. The evidence for it on larger scales is overwhelming. But it does challenge the assumption that every galaxy must follow the same rules. How do you build a galaxy without the scaffolding that's supposed to be required? These oddities are rare, but even a few exceptions can crack open a theory. When a massive galaxy sits precisely in front of a much more distant one, something extraordinary happens. The gravity of the foreground galaxy bends the light from the background galaxy, warping it, magnifying it, and in perfect cases, sculpting it into a complete ring. An Einstein ring, a circle of light, bent by gravity, predicted by general relativity over a century ago and now observed in stunning detail. Some of these rings are almost perfectly symmetric, smooth, unbroken arcs of light that look too precise to be natural. And in a way, they are. The symmetry of the ring is a direct map of how mass is distributed in the foreground galaxy. Every imperfection, every slight asymmetry in the ring tells you something about the distribution of dark matter, the shape of the galaxy's halo, the presence of substructure. These rings are not just beautiful, they are instruments, and reading them with precision is an art that astronomers are still refining. Far beyond the bright disk of a galaxy, in the faint, thin outskirts where starlight fades to almost nothing, telescopes have sometimes caught something unexpected. New stars, forming in the dark, quiet edges of galaxies, far from the dense clouds and busy spiral arms where star formation normally happens. How did cold gas get out there? How did it survive without being heated or dispersed? And how did it manage to condense and ignite in a region so sparse and so remote? Some of this gas may have been flung outward by gravitational interactions. Some may have drifted in from the intergalactic medium. But the process that turns a thin wisp of cold gas in the outermost edge of a galaxy into a newborn star is still being worked out, one faint blue dot at a time. Not all massive galaxies spin fast. You'd expect them to. They've had billions of years of mergers and interactions that should have imparted angular momentum. And many do rotate impressively. But some massive galaxies barely spin at all. They lumber through space, their stars moving in random, jumbled orbits rather than in an organized, rotating disk. These slow-spinning giants are thought to be the products of particular kinds of merger histories, multiple collisions from random directions that canceled out each other's angular momentum, leaving the galaxy with mass but little coherent rotation. Each one carries the fossil record of every collision it absorbed. But reconstructing those histories from the sluggish, disordered motion of their stars is like trying to reconstruct a conversation from the echo in an empty room. When hot, young, massive stars ignite, they don't just shine, they blow. Powerful stellar winds and intense radiation push into the surrounding gas, carving out vast bubbles and hollows. From a distance, these bubbles look simple, round shells expanding outward. But look closely and they are anything but. Filaments, sheets, arcs, lace-like patterns of glowing gas, sculpted by the interplay of winds from multiple stars, radiation pressure, magnetic fields, and the uneven density of the gas they're pushing through. Some of these structures look almost organic, like cell walls or soap bubbles frozen at cosmic scales. The physics that shapes them is well understood in broad strokes: fluid dynamics, radiation hydrodynamics, magnetism. But the detailed patterns, the specific lacework of each bubble, emerge from a complexity that no single simulation has yet fully captured. In the dense environments of galaxy clusters, some galaxies are being undressed. As they move through the hot gas that fills the space between galaxies, the pressure strips away their own gas, peeling it back, pulling it out, dragging it behind them in long, luminous streams. These are jellyfish galaxies, and the streams they trail are not just dead gas. Stars are forming in them, bright, blue, newborn stars, igniting in the stripped material as it flows away from the galaxy, creating glowing tentacles that stretch for hundreds of thousands of light years. The galaxy is being destroyed and creating at the same time. How the stripping process triggers star formation in the tails, how long the tentacles last, and what eventually becomes of these orphan stars born in transit, is still being modeled and debated. Orbiting the Milky Way and other large galaxies are some of the smallest, faintest galaxies in the universe. Dwarf spheroidals, tiny, dim collections of old stars, so faint they're almost invisible, held together not by their own starlight but by enormous amounts of dark matter. Some of these galaxies have dark matter to visible matter ratios of 100 to 1 or more. They are, in some sense, more dark matter than galaxy. And yet they persist. The tidal forces of the Milky Way should have torn them apart long ago. Internal processes, supernovae, stellar winds, should have blown their meager gas supply away, ending star formation permanently. And yet they endure, quiet and stubborn, orbiting like ghosts around their much larger hosts. Their survival is partly mysterious. Their very existence tests are models of the smallest scales of galaxy formation. Around some young stars, the story of planet formation seems to be moving too fast. The dusty, gas-rich disks that surround newborn stars, the raw material from which planets are built, normally take millions of years to dissipate. Slowly, the dust clumps into pebbles, then boulders, then planetesimals, gradually clearing the disk as planets grow. But around certain stars, the disk appears mature one moment and is simply gone the next, cleared out on timescales that are hard to explain by gradual planet growth alone. Something accelerated the process. Strong winds from the star, blowing the disk away. A massive planet forming quickly and sweeping up the remaining material. Or an unseen companion, a nearby star or brown dwarf, whose gravity disrupted the disk before it had time to evolve normally. The disk was there, then it wasn't, and the speed of that disappearance still catches astronomers off guard. Long, thin streams of stars trail through the halos of galaxies, remnants of ancient star clusters or small galaxies that were torn apart by tidal forces. These stellar streams are delicate structures, and astronomers have learned to read them like seismographs. Because sometimes the streams aren't smooth. They have gaps, wiggles, subtle density variations, as if something punched through them or tugged on them as they passed. The most exciting explanation is dark matter subhalos, small, invisible clumps of dark matter that gravitationally disturbed the stream as they passed nearby. If true, these ripples would be direct evidence of dark matter structure on the smallest scales, exactly where our models make their most uncertain predictions. But decoding which ripples were caused by dark matter and which by other gravitational effects is painstaking work. The streams whisper, and we are still learning to listen. And finally, scattered through the interstellar medium, there are clouds of molecular gas whose conditions don't quite make sense. Their temperatures are higher or lower than models predict. Their densities don't match the heating and cooling rates that should apply. Something is adding energy that we can't account for, or removing it in ways that don't show up in our standard equations. It might be cosmic rays, high-energy particles penetrating deep into the cloud and depositing energy. It might be tiny-scale magnetic reconnection events, releasing bursts of heat too small to observe individually but significant in aggregate. Or it might be chemistry, molecular processes that release or absorb energy in ways our simplified models miss. These clouds are the nurseries where stars are born, and we understand them well enough to describe the broad strokes. But the fine details, the exact temperatures, the precise conditions at every point, reveal that our picture of the interstellar medium still has gaps. Some stars breathe, not with lungs, of course, but with light. They swell gently outward, growing brighter, then contract again, dimming, then swell once more, over and over, with a regularity so precise it rivals a metronome. These are pulsating variable stars, and the most famous among them, the Cepheids, have a remarkable property. The speed of their pulse is directly related to their true brightness. If you know how fast a Cepheid pulses, you know how bright it really is. And if you know how bright it really is, you can compare that to how bright it appears and calculate how far away it is. This makes them cosmic yardsticks, standard candles that have helped us measure the size of the universe itself. And yet, the internal physics that drives the pulsation, the precise way layers of gas inside the star absorb and release energy, heating and cooling in rhythm, is still being refined. We use these stars to measure the cosmos, and we still don't fully understand the engine inside them. Some aging stars wear their history on the outside. As certain elderly stars approach the end of their lives, they don't shed their gas all at once. Instead, they release it in episodes, quiet, periodic outbursts that send thin shells of material expanding outward, one after another. Telescopes have revealed these shells as delicate, almost perfectly spherical layers of gas, nested around the star like rings inside a tree trunk. Each one marks a moment when the star exhaled. But what triggers these outbursts? They come at intervals that suggest some internal clock, thermal pulses deep in the star's core, perhaps, but the timing isn't always regular, and the shells are sometimes more symmetric than the physics seems to allow. These dying stars are writing their own obituaries in concentric rings of gas. And we can read the rings, but we can't always explain what set the rhythm. And then there are galaxies that wear rings too, more than one. A few rare galaxies display 2 or even 3 distinct rings of stars and gas, nested inside each other like the layers of a target. Each ring represents a resonance, a gravitational sweet spot where orbiting material piles up. But getting multiple rings to form, and to remain distinct and stable, requires a very specific combination of internal dynamics and external history. A past collision, perhaps, sending waves through the galaxy's disk that froze into concentric structures. Or a particular pattern of gravitational resonances created by the galaxy's mass distribution. Each double-ringed galaxy is a gravitational sculpture, and the precise chisel strokes that carved it are still being modeled. Some of the busiest places in the universe are also the most hidden. Deep inside thick clouds of gas and dust, stars are being born at furious rates. Dozens, hundreds of new stars igniting in regions so dense that visible light cannot escape. These nurseries are invisible to our eyes, but switch to infrared or radio wavelengths and they blaze. The dust that blocks visible light absorbs it and re-emits it as heat, glowing brightly at longer wavelengths. This is where we find the universe's most prolific star factories. But understanding what happens inside them is difficult precisely because they are so hidden. How does energy move through such dense environments? How does radiation from newborn stars interact with the dust and gas still surrounding them? How much of the light escapes and how much is trapped, recycled, and re-emitted? We can see that these nurseries are extraordinarily productive. But peering through the dust to understand exactly how they work remains an ongoing challenge. High above and below the flat disks of some galaxies, long arcs of stars trace graceful loops through otherwise empty space. These are stellar streams, the stretched and shredded remains of smaller galaxies or star clusters that were captured and torn apart by the gravity of the larger galaxy. Each stream is a fossil orbit, tracing the path its parent object followed as it was slowly unraveled over hundreds of millions of years. Some loop nearly perpendicular to the galaxy's disk. Others wrap around multiple times, like thread winding loosely around a spool. By studying their shapes, astronomers can reconstruct the gravitational field of the galaxy that destroyed them, mapping dark matter by the scars it leaves on its victims. But matching each stream to its original parent, reconstructing the orbit in full, and accounting for every gravitational influence along the way, that work is still far from finished. In 2017, something fell through our solar system that had never been seen before. An object from interstellar space, a visitor from another star system, passing through on a trajectory that would carry it back out into the void forever. It was named Oumuamua, and its shape, its behavior, and its origin were immediately debated. Then, in 2019, a second interstellar visitor arrived, Comet Borisov. This one more clearly a comet, trailing gas and dust as it swung past the sun. 2 confirmed visitors in just 2 years. The implication is that interstellar space must be filled with these wanderers, comets and rocky bodies ejected from their home systems, drifting between the stars for billions of years before, very occasionally passing through ours. How many are out there? What can they tell us about the planetary systems that made them? We've barely begun to answer these questions. The deep space between stars may be far less empty than we ever imagined. Some planets are barely there. Not in the sense that they're small, they can be as wide as Jupiter or wider, but in the sense that they have almost no substance. Superpuffs, astronomers call them. Planets with densities so low that if you could somehow place them in water, they would float like cotton candy. Their bulk is mostly atmosphere, vast, extended envelopes of hydrogen and helium, puffed up to enormous sizes around a relatively small core. How do such delicate worlds form? And more puzzling, how do they survive? Close to their star, the intense radiation should be stripping that atmosphere away, peeling it back layer by layer. And yet some superpuffs persist, orbiting happily in environments that should have deflated them long ago. Either something is replenishing their atmospheres, or something about their structure makes them more resilient than we expect. They are planets that seem too fragile to exist. And yet they do. Stars slow down as they age. This is one of the cleaner rules in stellar physics. A star is born spinning fast, and over billions of years, its magnetic field acts like a brake, gradually bleeding away angular momentum. Measure a star's rotation, and you can estimate its age. But some old stars don't follow the script. A few ancient stars spin faster than they should, as if something spun them back up. Others rotate more slowly than even the most aggressive braking models predict. For the fast ones, the explanation might be dramatic. A companion star transferring mass and angular momentum, or a planet spiraling inward and being swallowed, its orbital energy briefly reviving the star's spin. For the slow ones, something about the magnetic braking process may be more complex than we assumed. Either way, the rotation of old stars is supposed to be one of our most reliable cosmic clocks. And some of those clocks aren't keeping the right time. When a small galaxy drifts too close to a larger one, it doesn't always end in a dramatic collision. Sometimes the encounter is gentler. The larger galaxy's gravity reaches out and slowly pulls the smaller one apart, stretching it into long, faint tails of stars that extend softly into intergalactic space. These tidal tails of dwarf galaxies are among the most delicate structures in the universe. So faint they were invisible until modern telescopes learned to look for them. Each tail tells the story of a slow dismemberment. The shape of the tail, its length, its curvature, all of these encode information about the gravitational field that created it, the mass of both galaxies, and the orbit of the encounter. But these tails are fragile. They fade, they dissipate, and comparing their subtle shapes to simulations, trying to match theory to observation, is painstaking work. The universe destroys small galaxies quietly, and the evidence disappears almost as softly as it was created. And finally, imagine a distant star shining steadily in the background of the sky, and then, for a few days or weeks, it brightens. Not because anything changed about the star itself, but because something dark, something invisible, passed between us and that star. The gravity of the unseen object bent the star's light, focusing it, amplifying it briefly before the object moved on. This is gravitational microlensing, and it is one of the few ways we can detect objects that produce no light of their own. Rogue planets, faint brown dwarfs, isolated black holes drifting through the galaxy. Each microlensing event is a momentary shimmer, a brief brightening that lasts days or weeks, never to repeat in exactly the same way. From that shimmer, astronomers try to extract the mass of the invisible object, its distance, its speed. But each event gives only partial information. The shimmer is real. The object was there. But turning that fleeting signal into a clear identity remains one of the most delicate puzzles in observational astronomy. And with that, we've drifted through 100 mysteries of the deep cosmos. If sleep has already found you, then the universe did its job tonight. Rest well. But if you happen to still be awake, your mind still quietly turning, you might enjoy drifting into one of our other journeys. There's one on cognitive biases, on the strange, invisible ways your brain fools you every single day without you noticing. I hope you sleep well. Good night.